Second example from Stokes theorem. Now in this example we want to calculate this flux integral where f equals to the vector field f equals to z comma negative 2x comma xy, and s is the part of our surface is the part of this downward paraboloid above the xy plane. And here is a picture. So the surface has the equation c equals to 4 minus x squared minus y squared, and it's above the xy plane. So we can have this black colored boundary. That's the boundary of the surface. And now we want to use Stokes theorem to calculate this flux integral. Now in this example what we do is the opposite of the previous example. So instead of calculating this flux integral, now we calculate the equivalent line integral. So if you recall the Stokes theorem says f dot ds over a closed curve C equals to the flux integral of curl f dot n ds with the surface S. So now instead of calculating this right hand side, we calculate the left hand side. Now we all know from chapter 13.2, we all know how to calculate the line integral of a three-dimensional vector field. But before we do that, we want to parameterize this curve C. Now the equation of this curve C is now on the xy plane C coordinate equals to 0. Therefore the equation of this boundary C should be 0 equals to 4 minus x squared minus y squared. This is nothing but a circle with radius 2. Circle with radius 2. To parameterize the circle, so if you recall polar coordinates, we know that x equals to r cosine theta, so let's use the parameter t instead of theta, and y equals to r, let's say sine t. Now in this case we have a fixed radius 2, this is 2 cosine t, y coordinate is 2 sine t. So now the parametric equation of the boundary C is 2 cosine t comma 2 sine t. And now let's find the limits for t. T goes from 0 to 2 pi. If t equals 0, you will get 2 comma 0, and then when you increase c, your curve will traverse in the counterclockwise direction. The direction is very important, okay, because we need a positively oriented curve that traversed counterclockwise direction. Great. So now curl of f dot n ds, this flux integral over the surface S equals to the line integral over the closed curve C. Okay, now how did he define the line integral? So we have this vector field f dot c prime t dt, and t goes from, let's say, a to b. Okay, so now we need c prime t. Okay, let's calculate c prime t. minus 2 sine t and 2 cosine t. Of course, our vector field is in three-dimensional space, so let's slightly change the parameterization. The third component should be 0, because now we are on the xy plane. Okay, so now this line integral becomes 0 to 2 pi, integral from 0 to 2 pi. And what was f? Okay, so the vector field f equals to this. Let's see vector field f. Dot c prime t, which is negative 2 sine t 2 cosine t comma 0 dt. Now one thing you should know is when we evaluate this line integral, we have to evaluate this vector field f on the curve C. Now on this curve C, your C coordinate equals to 0. So now what we have is this should be 0 comma negative 2x comma xy dot negative 2 sine t comma 2 cosine t 0 dt. But on the curve, your x coordinate equals to 2 cosine t and y coordinate equals to 2 sine t. Okay. And if you do this dot product calculation, you will not get a contribution from the product of the first component, because it's 0 times negative 2 sine t. Similarly, we will not get a contribution from the third component, 0 times xy. And we only get a contribution from the third component, the second component, which is negative 2. What is your x? X coordinate is 2 cosine t times another 2 cosine t term. So basically we have negative 8 cosine squared t dt. Now to integrate cosine squared t, we use the half angle identity. You know that cosine 2 theta equals to 2 cosine squared theta minus 1. This means cosine squared theta should be cosine 2 theta plus 1 over 2. Okay, so instead of integrating cosine squared theta, now we can integrate this term. You will get negative 8 times the integral from 0 to 2 pi of cosine 2 theta plus 1 over 2 d theta dt. Sorry, we use t, so this should be t as well. Okay, so we have negative 8 over 2. Integral of cosine 2t should be sine 2t over 2 plus integral of 1 is t if you apply the upper limit and then the lower limit, you will get, so here you will get sine 4 pi, which is 0, minus sine 0. So we do not have a contribution from this first term, but if you consider the second term, you will get 2 pi minus 0, which is 2 pi. So we have negative 8 over 2 times 2 pi, which is same as negative 8 pi. So here we use Stokes theorem to calculate a flux integral, but this time what we did was, instead of evaluating this flux integral, we consider the corresponding line integral and we solve this line integral.